All right, pre-calculus kids, we're looking at section 7.2 on logarithmic functions. Section 7.1 was on exponential functions. And guess what? They're inverses of each other. So there's going to be a lot of similarities in the way that we treat them and the way that we work with them. So a couple things you need for today's lesson. You need a calculator. It just has to be a scientific calculator, not necessarily. Actually, I take that back. It has to be a graphing calculator, so maybe a Desmos for you to be able to see it. I'm going to show you how to do it on the graphing calculators that we have, the TI-83s, but you can do it on Desmos as well. So you need that, and you also need a highlighter. At least I'd recommend a highlighter. All right, so what the heck is a logarithm? And there's a whole thing here that y equals the log base b of x if and only if b to the y equals x. So this is a conversion thing. There's a couple factors. B has to be bigger than 0, b can't be 1, and x has to be greater than 0 with all of these things. So one of the ways that we transfer or we write from a logarithm to an exponent or an exponent to a logarithm is using this rule. So I'm going to write it up here because it's kind of important. If I have the log y equals the log base b of x and I want to turn that into an exponent, all I have to do is rewrite it as b to the y equals x. And I'm going to show you a way for us to do this that's going to make it a little bit easier. It's with a loop. Man, that's the worst looking arrow I think I've ever seen. Let me fix that. I was trying and it just wasn't working right. All right, here we go. Try again. Redo. I don't know, that's a whole lot better, but you got the idea. All right, so anytime you want, if they give you an exponent and they say turn it into a log, you go like this. Just take those pieces and put them in the right order. Anytime they give you an exponent and they say turn it into a log, all you have to do again is convert it this way. So whatever the power is gets equal by itself, and then log base b of x. All right, so this rule here is really important. This is where my first highlight comes in, which is the same thing that we just wrote in the top of the page. Now on the video for the curriculum, how does Mr. Bean say log base b of x? He says literally, quote, log base b of x, and that's what we're going to say too. How does Mr. Kelly say it? He says this, and we're not going to use this method, but here's what he says. Maybe you might like it. The exponent I use on b to get x. That's too much for me. That's just too much for me. So I like this. Log base b of x makes more sense. These functions are inverses of each other. It's funny they put this in small print because really that's an important fact. Recall an exponent function. Actually, I guess I should say exponential. An exponential function is of the form y equals b to the x. A logarithmic function, second blank, is in the form x equals b to the y. Remember what we do with inverses, how you switch the x's and y's? There you go. If they're inverses of each other, then all I did was I switched the x's and y's. So the first questions they're going to ask us to do is to take this guy and rewrite it as an exponent. So that means that I'm going to get rid of the log. I'm going back up here to the top of the page. I'm going to get rid of the log, and I'm going to write it like this. So let's see if we can decipher the pieces. B is the base. That in my problem is a 5. I'm going to put it over here. Y is whatever's on the other side of the equal sign by itself. That would be the 3. And then the x is the piece right here that's next to that base, equals 125. And there you go. Is that a true statement? Sure it is. And they always will be. They're not going to give you one that doesn't work. But here's another way, and this is the loop method. This is the Wenner loop. If you start with the base and make a loop Now I made the loop so you could see the numbers. That tells you exactly how you need to set it up. It's going to be 5 to the third equals 125. Done. It almost makes it so you don't have to remember this rule, right? So anytime you're trying to write it as an exponential form from a logarithm, just start with the base and loop it around. There's a Jimmy Fallon song on YouTube that's all about the base, you know, with Meghan Trainor. And I played it last year for the class, and they were all like, that was really not very good. So I won't make you suffer with Jimmy Fallon's All About the Base, but if you're interested, you can go to YouTube and look it up. All right, that's it. That's how you do it. Now they say, okay, now rewrite this as a log. Now they're going the other way. They're giving you the exponential side, and they want you to turn it into the logarithmic side. So let's see if we can figure this out. First of all, before I even do that, what's the deal with a cube root in the midst of this? So this is like 1/8. Do you remember how roots go? If I write it as a power, it would be, if it were square root, it would be to the 1/2 power. Because it's a cube root, it's to the 1/3 power equals 1/2. So there's my exponential form so that I can set it up correctly. We didn't want a square root or a cube root in this case in the problem. That would not be helpful to us. All right, so let's see if we can decipher it. Let's decipher it. I need an log. Well, first of all, what's the y piece? The y piece is the power, so I've got a 1/3. And then I have an log. And then the base is whatever is inside here, so that's 1/8. And then I have a 1/2 out here. That looks really, I'm sorry, yeah, 1/2 there and the 1/3 on the other side. But guess what? The loop method works with this too. So the loop method starts with the 1/8, goes to the 1/2, and stops at the 1/3. 1/8 is the first thing you base, 1/2 is the next thing you write, and it equals 1/3. That 1/3's in a weird place. I could leave it on that side, or for the sake of the loop, I can toss it on the other side, make it over here with the 1/3, just to make it easier. So 1/8 as your base, 1/2, 1/3. All right, here we go. Evaluate without a calculator. So for all of these, I'm going to set them equal to x. Make it equals x. Actually, I'll do it all the way across. These are logarithms. I want to write them as exponents so that I can solve them. That's always going to be the case, by the way. If you're solving a logarithmic equation, you use exponents. Turn it into an exponent. If you're solving an exponential equation, you're going to turn it into a logarithm. They're vice versa all the time. Remember, they're inverses. All right, so let's try the loop method. Loop method with this. Start with the 2, go to the x, go to the 8. What would that look like if I write it? 2 to the x equals 8. All right, we'll think about that logically. 2 to what power equals 8? And I get an x that is 3. 2 to the third. 2 times 2 times 2, 3 times, gives me 8. If I apply the same loop method to this guy, start with 8, goes to the x, goes to the 1/64. So I have 8 to the x equals 1/64. Well, that one's a little more tricky, right? Because really this guy, the 1/64, 64 can be written as a power of 8, 8 squared. So this would be like 8 to the x equals 1/8 squared, because that's in the denominator. I'm going to run out of room. I'm going left. 8 to the x equals 8 to the -2. Remember that rule? If it's in a fraction, if it's in the denominator, it can be written as a negative. So now think about this. Remember, we got like bases. What do you do with the powers? You just set them equal to one another, and I get x is -2. That's going to be my answer for number 4. Same method for number 5. 8 to the x equals 1. Well, that's one of the properties of logarithms. Remember, if it's to what power are you going to get a value of 1 out? And we know that anything to the 0 power is 1. All right, so let me go to the next thing I want to show you are rules for logarithms, properties of logarithms. But before I show you that, I want to remind you of some properties of exponents. So say, for example, I have, what do I want to say here? 2 to the 4th, I'll make it, times, that doesn't look like much of 2 to the 4th times 2 to the 3rd. 2 to the 4th times 2 to the 3rd. What do you do with those exponents? Like bases, multiplying the pieces together, you add them. So you got 2 to the 7th. What if I had 2 to the 4th over 2 to the 3rd? What do you do when you are dividing like bases? You subtract the powers. You get 2 to the 1st. Well, guess what? That same concept of properties applies to logarithms. If I'm adding the if I'm multiplying the bases, I add the exponents. If I'm dividing the bases, I subtract the exponents. But these are now logarithms. So when I'm looking at this, it's based off these same properties of what you have with exponents, but now you're applying it with logarithms. So the next one says, all right, expanding and condensing. So there are, if I look at this thing, I have a 3, I have an x to the 5th. Oh, by the way, the last one says that anything with a power, the power can come down in front of that logarithm. That's the rule. So 3 rules. Adding, when you multiply, you add. When you divide, you subtract. And when you have a power, the power comes down in front. They're your 3 things. So back to number 6. I have a log base 4. I have a 3 piece, I have an x to the 5th piece, and I have a y piece. I have 3 pieces. So when I go to expand this, which is what you're doing for number 6 and 7, when I go to expand it, I'm going to have 3 pieces in my answer. And I'm going to start over here because these tend to be long in the midst of writing them. So I have 3 pieces. They're all going to be log base 4. Oh my gosh, my pen is running out. So sad. Let me see what this guy does. Log base 4. I'm going to write that 3 times because I've got 3 pieces. I'm going to leave a space. Log base 4. And I'm going to do a log base 4. And you can't see me, so let me move me so I can see you. Well, the first piece is a 3. Okay, there it is. There's my 3. These are all attached by multiplication. And if they're attached by multiplication, then I know I need a plus sign. X to the 5th, what happens with that power? The power is allowed to come down in front just like this property rule says. So it's going to be a 5 and then a log base 4 of x. See how the power is now in front. And then I have a y that's being multiplied by it, so I need a plus. Y doesn't have a power, so I don't need a number in front. There's my y. So 3 pieces, each one gets their own log base 4. By the way, with our highlighters, this is an important box. Right here. We didn't box it in yet. Okay, next one. Before I go into how to expand it, I have, by the way, 2 pieces, a p piece and a q piece. But let's take this p over q to the 4th, and then being raised to the 5th power, a power to a power, you're going to multiply this out. So really, let's simplify this a little bit before we expand it. Log base 3. What's my p's power? It's really a 5th power, p to the 5th. What's my q's power? Q to the 4th to the 5th. I have to multiply those. So this one's going to be q to the 20th. That's a big old power. I have 2 pieces. I have a log base 3. And I have a log base 3. Each one gets their own little log. 2 pieces. P piece. P has a power. Power's 5. Where's the power go? Power goes in front. 5 log base 3 of p. That takes care of the numerator. Now this time I am dividing these things, which means that I'm going to have a subtraction sign instead of having a plus sign. It's my plus. Q to the 20th. Where's the power go? Power goes in front. 20 log base 3 of Q. And now that guy's done. He's expanded. So each variable and number gets their own log based off of whatever log they give you. If they give you log base 2, log base 3, whatever it is. And then the last one they want you to do here is to expand this thing. This one, they were not very nice to you. I can tell you that. So let's see if we do one thing at a time. By the way, these have to be like bases or you can't work with them. You can't condense them, put them all as one. They have to be all the same base. Like if these were base 4 and this was base 8, they'd be separate entities. So they have to be all the same base for you to be able to condense them into one thing. And what is that base? That base is a log base 4. So I'm only going to write this once now. You're condensing. You only want one of whatever this is. This one's a log base 4. All right, well, let's figure out what they gave you. They gave you an 8 minus a 5. Well, 8 minus a 5 means that you're really dividing them. So that's 8 over 5. And you say, but wait, there's a 2. And where's that 2? That 2's in the front. So that represents actually the power on this whole thing. So that's going to be a square that's there. Then I have a plus sign. What do plus signs mean in our world of logs? They mean to multiply. So I'm going to have a times. And then I have 25. And that 25, see the 0.5 that's in front? That's the power on it to the 0.5. Now you've just condensed that technically, but I guess we could take that a little bit further. Let's see if I did that. That would be, I'm going to come up to here to condense log base 4. Only write it once. This is, I'm going to come over here with this. This is going to be my final answer up here. 8 squared is 64. 5 squared is 25. That takes care of this. 25 to the 0.5, 25 to the 1/2, that's like the square root of 25. So that's times 5, square root of 25. You can check it out in your calculator. And the 25 and the 5 can reduce, so I end up with 64 over 5 as my best condensed answer. Log base 4 of 64 over 5. That's expanding and condensing. And by the way, we're going to be doing quite a bit of worksheet practicing with this because there's a whole lot of information in this whole thing. So they only gave you 1 or 2 examples of each thing. All right, next one, change a base. Change a base, numbers 9 and 10. Change a base formula. What happens if they are different bases? What happens if you can't put them together like you normally would? And that's what numbers 9 and 10 deal with. So if they're not like bases, and in fact, back when you were working with I guess this is kind of, number 11 explains what I'm thinking of. Remember when we did the section 7.1 and we got like bases for the numbers? What happens when you can't get a like base? Like if this 41 were a 49, you'd be like, yeah, no sweat. The answer is 2, x is 2, because 7 squared is 49. But what happens when it doesn't break down into the like base? And that's where this change of base formula is coming from. So here's what it says. If you have the log base c of a, take the log of the larger printed number. I'm talking about the font size. The larger printed number divided by the log of the base.
Bye.
Bye. Have a great day. All right, so I'm going to set this up using change of base formula. Here I am. Take the log of the larger printed number, the 5, divided by the log of the subscript, which is 12. And you say, yeah, that doesn't look any better, Wenner. So here's where your handy-dandy calculator comes out. Some of you have the blue calculators. You're going to second PRB, and that pulls up the logarithm menu. And what you're looking for is LOG. Now on this calculator, maybe I can show you the whole thing here. Oh, there it is, Mr. LOG down here. So I'm taking the LOG of 5, and notice how it opens parentheses. So I want to close them up and then divide by the LOG, hit it again, of 12. and then press enter, and that gives you your answer. So 0.648, if I were a rounding girl. Pre-calc, we like to do 3 decimals. Kind of like the standard for our calculus and pre-calculus kind of stuff. If I do number 10, same way. LOG, larger printed number is 20. Little subscript guy is a 2. And so I go to my handy dandy calculator and I do the same thing. Log of 20. LOG 20. Close it up. Don't forget to close that parenthesis. Divided by LOG 2. And I get 4.322. 4.322. If you're having trouble with your calculator finding the buttons, just holla when we get into class time and I can show you how to make it work. All right, here comes the other way. That's when you have a logarithm. What happens when you've got an exponent? There were 3 methods that they showed you in the curriculum video on how to do this. I am only going to show you the 2 because this one in the middle, I can show you. Well, I'll show you in a minute. Let me show you the first method, the last method, and then I'll just give you a clue as to what this middle method is. All right, so here's what I've got. If I have an exponent, in order to solve it, I have to turn it into a logarithm. So this one I'm going to do the log of 41, which, by the way, I'm going to go into this box I'm not going to use, so I'll have enough room, equals what happens with the power. The power comes down in front, x log of 7. Now, how would you solve for x? Well, x is attached to the log of 7 by multiplication, so you're going to divide by it. So you're going to get x equals the log of 41 divided by the log of 7. And so isn't that just the same thing you were doing over here back at number 9? So you're going to go to your handy dandy calculator and you're going to divide them out, and you get an answer of 1.908. Now, there's another way you could do it on your calculator, and that is with the graphing feature of your if you're using, or Desmos, go to Desmos, same idea. If I go into y equals and I put my 2 functions, I just put 41 as one of them, and I put 7 to the x as the other one, and I graph it. Now, what's going to happen with mine is that my window, Desmos makes this much easier, but my window only goes to 10. I can't see that other line, so I need to get taller to be able to see the 41. So I'm going to hit my window button and I'm going to make my y's taller. I'll make them go to 50 because I'm trying to get to 41. So here goes my graph this time. Ooh. That made my 7. Oh, there it is. Cool. All right, you can see that pretty clearly. All right, so what you're going to do is hit the second trace button, and that pulls up this menu of many things. And you want to know where they intersect, so I'm going for number 5. And it says first curve, and you're like, yeah, that's on 41, cool. And then you say second curve, and it's on the 7 to the x, and I can tell that from up in the corner what it's blinking on. And I'm like, yeah. And they, men inside, they have such a sense of humor here. Guess? Of course I want you to guess. I want to know what it is. And there it is. 1.908 is what you get. The coordinate is 1.908, 41. So graphing it, if I put y1, and I'll put it in our little box here, if I put in my y1 of my calculator, or in Desmos, whatever it is, my second graph, I put in 7 to the x, and then I figure out where they intersect. That gives me the coordinate 1.908 and 41. Whatever this x value is, let me circle it in a different color. Whatever the x value is your answer. Same answer you got when you did it with the logarithm method. So you could graph them and figure out that point of intersection, and some of the homework problems will have you do that. All right, let me show you the one we're going to skip. Here's what it looks like. This is Mr. Bruce's way. He takes the log base 7 of 41 and the log base 7 of 7 to the x. And then from there, he pulls the x down in front. So log base 7 of 41 equals x log base 7 of 7. And then he does the change of base formula to it. That just seems like a whole lot of extra steps that we don't need to talk about. So we're not going to use that method to be able to do these. We're just going to keep it with, take the log of both sides or graph it. We'll keep it easy. All right, next one, same kind of question. Now we have 0.25 equals 2 to the x. Take the log of both sides. So I go the log of 0.25 equals, pull the power down, x log of 2. Solve for x, divide by log of 2. X equals the log of 0.25 over the log of 2. Go to your handy dandy calculator and calculate it out. Comes out to be -2. I showed you the graphing way. This one you'd put y1 as 0.25. You'd put y2 as 2 to the x. And then you'd figure out where they intersect. Comes out to be, lo and behold, -2. Go figure. All right, there's page 1. Woohoo! Page 2. So they give you some rules for logarithms. And if I have b raised to what power am I going to get b back? And that's to the first power. B to the first is b. B to what power is 1? You say 0. If I have a b to the x, that your answer is x. And basically the logarithms and exponents undo each other. See how you have an exponent and a logarithm? Same thing here, you have an exponent and a logarithm. They undo each other. Your answer is x. Log base 10 is called the common base. Common base. And log base e, that's actually more likely seen as the ln of x. ln, natural log. He's considered the natural logarithm, ln of x. Its base is e. All right, here goes. Solve for the unknown variable, number 14. See how there's an invisible, there's no number there? This is what we're talking about with this stuff. If there's no number there, it's understood to be 10. That's the common base. It's invisible. Kind of like, you know how you have a 1x? We don't necessarily put the 1 there, but it's understood to be there. Same concept. This one with logarithms, the common base is a 10. So now we're going to change that to an exponent. If you want to solve a logarithm, you have to change it to an exponent. So we're going to loop. Whoop. There's my loop. That means that 10 to the 3.0876 equals x. Well, can you solve that? Do you know what that looks like in your calc? Oh no, we're going to figure it out. Take your calculator. And I want to know what 10 caret 3 point, put it where you can see it, 3.0876 is. And we get an answer of 1223.488. And there you go, 489, I guess, really right. So this is x equals 1223.489. You solved it. You got it. Next one, see how they have an ln there? Well, ln has a base of e. Remember e from our exponents? This has an invisible base of e. So that when I do my loop this time, looks like that, I have e to the negative 0.9128 equals x. I go to my handy dandy calculator. Do you remember where e is? I think most of you are using that the blue calculator. So again, you're going to second PRB. For me, it is second and then the ln button. And again, if you can't find these things on your calculator, we can chat in class. So there I go, e to the negative 0.9128, and I get an answer of 0.401. All right, 0.401. They wanted you to get a picture of what the graphs look like. So if this isn't b to the x, this is an exponential graph. Remember, we've seen those before. If I take and talk logarithms, graph the logarithmic graph for this, if this coordinate is 0, 1, what happens for my inverse? My inverse has to be 1, 0. Remember, you switch the x and the y? And if this one is b, this one's really at like 1, 2, then I would have one at 2, 1. And so what this graph actually looks like, and this is every logarithmic graph, kind of has the same deal. It skates along the y-axis and then it goes off this way. It curves. Probably curves even more than that, than what I drew it as. But anyway, this guy is y equals the log base b of x. Logarithmic graph. How about if it's a negative? Or if I have a fraction as my power here. Same thing goes. 0, 1 becomes 1, 0. And then I'm looking for the 1 over b is kind of hard to see on this one. But here's where it goes. This one skates along the y-axis this way and then does its turn this way. Now if you remember graphs of inverses, they're always going to be reflections over the line y equals x. That's why they put that on there, where you fold it over that line and you're going to get the same thing when you look at it. Fold it over, they match up with each other. All right, last set. 16 to 20. Use the properties of logarithms to find the inverse of the given function. Hint, switch x and y and solve for y. All right, so let's try that. F of x, remember the rules for inverses. Number 1 was change the f of x to a y. Same thing, y equals 4 to the x. Switch the x and y. X equals 4 to the y. Solve for the new y. Now here's where the issue is, which makes this different than what we've done before. Where's the y? Well, the y is up in the power, and the only way to undo that, to bring the power down, is to use logarithms. Remember the rule that the power is allowed to come down in front when you take the log of both sides, and that's what we're doing. The log of x equals y log of 4. How do you get the y by itself? Divide by the log of 4 because they're attached by multiplication, so you're going to have the log of x over the log of 4, and that's what it equals. You're done. Y equals that. Now you don't have to call it the inverse on these like you did back in the day. I guess you could. After the -1 is your notation, but they don't make you do that for this. So let's see what we got. Here comes the next one. Y equals 3 to the 2x. Switch your x's and y's. X equals 3 to the 2y. The y is up in the power. How can you bring it down? Gotta log both sides. Log of x equals 2y log of 3. Now let's work on getting the y. All right, first thing, I have a 2 that's being multiplied with it and a log of 3 that's being multiplied with it. So I'm going to divide by those. Gives me y equals the log of x on top and a 2 log of 3 on the bottom. A little messy because the y was kind of sandwiched in the middle of it all. But they're all attached by multiplication, so it's just a division thing to get rid of it. All right, next one. Y equals 5 to the 1/2 x. That's really brutal. Switch them around. X equals 5 to the 1/2 y. Where's the y? In the power. Do the logs. Log of x equals 1/2 y, the power, times the log of 5. Log of 5. Let's just do the log of 5 first, because that 1/2's a little messy. Log of x over log of 5 equals 1/2 y. How can you get that 1/2 out of there? You can multiply both sides by 2, right? So that's going to give you 2 log of x over log of 5 equals y. And that's really your answer. However, they could, if they wanted to, write it like this, and this would be also the same thing. That 2 in front represents the power, so this could be like x squared. This would be an equivalent form. I guess we could have said that back here with this guy too. This would be the log of 3 squared, if you wanted to write it that way. Okay, 19 and 20 are different. 16, 17, 18 were very similar. 19, 20 are a little bit different. I start out the same. Y equals the log of x plus 1, right? Then switch your x's and y's. X equals the log of y plus 1. I'm trying to dig towards this y. So the first thing I'm going to do is try to isolate the term that has it. So I'm going to take this 1 and put it on the other side. That makes this x minus 1 equals the log of y. Well, how can you undo a logarithm? And you say, do you say? You say, turn it into an exponent. What's the base? There's an invisible 10. Invisible 10 right there. How do you go about that? Now this one's kind of in the wrong order. It's kind of a weird one. But it goes from the 10 to the x minus 1 and then to the y. I loop it. So it's going to be 10 to the x minus 1 equals y. And I have just solved that for y. Kind of interesting, right? If it's a logarithm, turn it into an exponent. Exponent, turn it into a logarithm. Last one. This one is slightly easier than the others if you catch it. I'm going to take this thing and I'm going to switch the x's and y's. Because I don't have an f of x this time. So it's going to be the ln of x equals 2 ln of y. Or I could say the ln of x equals the ln of y squared, right? That's what this 2 in front means. Now think about this. This one's different than the others because see, I have an ln on both sides. This was only a single-sided log. This is on both sides. So the log of this equals the log of that. In order for that to happen, then these two, the x and the y squared, have to be equal to one another. So I can just ignore the logs. I don't need to do any of that stuff with this one because the ln was on both sides. By the way, if one side's an ln and one's an log, no go. Can't do it. It's because they're both the same thing that I was able to just ignore them. Now how do you solve for y for this? I've got to square root it, right? So I've got the square root of x equals y. And that's your answer. Did you solve for y? Yep, you did. You got it. Okay, a few example problems, and then we are done ski with this section ski. All right, flip into the practice problems. Numbers 1, 2, and 3 we are not doing. They're talking about right triangles and special right triangles at that, back in geometry. We're going to start with number 6. This is expanding and condensing. In this case, expanding. Numbers 1, 2, and 3. All right. Before I even go there, I want to figure out what's the real power on the x, what's the real power on the y, and what's the real power on the z. I've got to figure that out. Log. X is being raised to the third power, so this is an x cubed. Y is squared. I'm sorry. That's not true. Say go back, wait a minute. Yeah, if I look at this, see how the squares outside the parentheses that include the x? That means the x is being squared as well as being raised to the third power. So if I'm squaring it and I'm raising it to the third power, I'm really to the 6th power. That's better. Same thing goes for the y. Y squared cubed, multiply the powers, I get y to the 6th. Z is being cubed, and so it's just a z cubed. Okay, that's what it would look like if I had all those powers written better. Now, how many pieces do I have? I have an x piece, a y piece, and a z piece. I've got 3 pieces. I'm going to write log 3 times. I'm going to come in this box so I have enough room. Log, leave a space. By the way, there's no base there. Understood to be 10. Log, leave a space, log. 3 pieces. I have an x piece, a y piece, and a z piece. What's the power on the x? It's a 6, goes in front. What's the power on the y? It's a 6, goes in front. What's the power on the z? It's a 3, goes in front. Now I got to decide if they're pluses or minuses. Well, the x and the y are being multiplied. Multiplied means plus. If I go to my z, that's in the denominator. That's being divided. He's on the bottom. He's a minus. And that's what it would look like expanded. All right, that's number 6. Number 9 was the next one I thought was kind of ugly, because look at this fraction at the end, this thing. What if I wrote it like this? What if I wrote it as the log base 3 of y plus 7 log base 3 of x. What if I wrote the last one like this? 1/4 the log base 3 of z. Is that the same thing? Is that my math legal? And it is. All right, so here we go. Condensing means you write it once. Log base 3. One time. I have a y. I have a plus sign. Means times. I have a 7 in front of an x. That means it's x to the 7th. Remember the powers in front. Oh, check it out. I got another plus. Times again. Z to the 1/4. And that's it. That's the whole thing. There's number 9. Now, the next sets, 10 to 12, they say use the bean method. That's the change of base formula. We're going to use the change of base formula for all of these up to 15. Remember, we're not doing this Bruce method. We're not going to do that. So the one I picked was 15. We're going to use the change of base formula to help us out. Actually, I don't know that I would necessarily call this the change of base formula, but this is when you have the power. You're going to take the log of both sides. So this is back like numbers. These guys. We're doing the same thing we were doing back with numbers 11 and 12. So I have the power is in the exponent. I want to get it down, and the only way I can do that is through logarithms. So I'm going to take and make this x log of 100. So I can bring that power down, equals the log of 50. How do you solve for x? You divide by the log of 100. X equals the log of 50 over the log of 100. I go to my handy dandy calculator and I put those in there. Log of 50 divided by the log of 100. Guess what pops out? 0.894 is what pops out. Now let's just play for a second with our calculator. If I take my calculator and I want to check my answer, well, let me plug it in and then you can see. We're saying 100. My answer was caret to the 0.894. Right? 100 to the 0.894. What should the answer be? Oh, there's an issue. Hold on. Interesting. Let's see. Let me see. Hold on. Let's go back. Maybe I was wrong. Log of 50 divided by the log of 100 Ah, it's 849. My bad, a little dyslexia going on there. 0.849, let's try that and check our answer. 100 to the 0.849. There we go. Should be an answer close to 50. How come it's not 50 exactly? And the answer is because we rounded 0.849. Because that's what it is. All right, let me fix my paper. My dyslexic switch there. 849. All right. Then he says, okay, well now do this by graphing. Now I kind of showed you one of those not that long ago, but just for kicks and giggles, I'll do it again. In y1, I want to put in 100 to the x. And in y2, I want to put in 50. Oop, not 50x, hold on. Clear, 50. I go to my graph. I don't remember what we put in there as our, oh, it might work. Can you see it at the top of the screen, what our window was? Sometimes you have to play with the window. Obviously, if you're doing this on Desmos, it's just a matter of scrolling in and out. It makes it pretty easy. I want to figure out where they intersect. Go to number 5 for me. Yes, I want you to guess. And there it goes, 0.84950. So right here, my point is 0.849. Oh, it was 10. Silly bean. Hold on a minute. Let me fix myself. I was all about that last problem. The second one needs to be a 10. There we go. I want to, well, we'll graph it first. My graph, there's 10. I want to calculate where they intersect, so I'm calculating where they intersect. First curve, second curve, guess. 0.5, that's better, 0.5. So this one is 0.510. And so x equals whatever the x value is in your coordinate, and your x value in your coordinate's a 0.5, and there you go. There's 18. Winner, how many more are you going to do? And I say, oh my gosh, 4. All right, 21 is next. 21, it says, find x, y, or b in this one, in these problems. So, if I do b, I'm going to pull the loop. I'm pulling the loop out of my pocket. If it's a logarithm, I need an exponent. So it's going to be written as b squared equals 16. Well, think about that. What number squared is 16? And y'all say 4. And you're right. Same thing with this guy. This one I'm going to loop-de-loop it. This one's a little more complicated. b to the 3/2 equals 1,000. I don't know about you, but I have no idea what that is. Which, by the way, the denominator tells you the root, and the numerator tells you what you're doing to it. You're cubing it in this case. But let's think about this back with our rules of exponents. I want to know what b is. To undo that 3/2, the only way I can do that is to multiply, like to make the power to it be the reciprocal of it. In other words, 2/3. Because what does that give me? That gives me 6/6. That's 1, b to the 1st. But whatever you do to the left, you got to do the same thing to the right, so this 1,000 has to go to the 2/3 power. I know it's a little complicated, but the only way you can undo that fraction is to multiply by its reciprocal so that you end up getting a value of b to the 1st. 6/6 would be first. And now I go to my calculator, I'm like, help me out, pretty please. What is 1,000 to the, parentheses, 2 divided by 3? And it tells me, oh, it's 1,000. Winner. 1,000 to the 2 divided by, ooh, parentheses. A 100, there we go. That's what it is. All right, that's 25. 28 has this whole inverse thing. Remember the inverse things we just were doing. Change the f of x to a y. 3 to the x minus 1. Change your x's and y's. 3 to the y minus 1. Darn y is up in the power. Only way to get to him is to log both sides. Log of x equals y minus 1. I'm going to put it in parentheses because they're all together. And then log of 3. Dig me out. I'm looking for the y. Get rid of the y, the log of 3. So that's going to the other side. So I have the log of x over the log of 3 equals y minus 1. Well, how do you get the y by itself? You're going to have to add 1 to both sides. So here I go. Final answer. Log of x over log of 3 plus 1. Okay. Last one is number 30. 30 says, find the inverse. All right, well, they don't have this one as an f of x, so I don't have to write the y. All I need to do is switch a Rooney. Log of x equals 3 log of y plus 4. I am digging to get to the y, so first thing I'm going to move is the 4. 4 is coming to the other side. So now I've got the log of x minus 4 equals 3 log of y. And what don't I like now? I don't like the 3. 3's got to go to the other side. 3's attached by multiplication, so I'm undoing that. I'm dividing. Log of x minus 4 divided by 3 is the log of y. Now this one is not as simple as one of the other ones we saw where there's a log on both sides, but there's extra smudge with it. So you can't just get rid of the log of both sides. I'm referring back to this guy. This one where we had the ln on both sides and it was just something simple. That was fine. I was able to just totally ignore that and not worry about it. But that's not the case in this one. This one's a little bit more complicated because it's got the divided by 3 and the minus 4. So here's what you need to do on this side, on this one. You need to turn it into a logarithm. I mean an exponent. It is a logarithm. You need to turn it into an exponent. This one's a lot trickier. Now if I do that, let me think about this way. I don't know that you would have thought of these guys the way that this one's going, but what if I said 1/3 the log of x minus 4? Right, because that 3 in the denominator is like dividing by 3. And if that's the case, watch this. This is an invisible base of 10 because it's an LOG. And I can loop this thing and turn it into an exponent. Start with the base. This whole thing's a power. Look at this. Talk about crazy. Here's it. It is going to be 10 to the, my whole power is this whole hot mess. 1/3 log of x minus 4. And that's what y equals. And that, my friends, is your solving for your using the inverse. That was hard. I tried to pick the harder ones on the page. Okay, so there you go. Section 7.2. Inverses, logarithms and exponents, inverses of each other. 7.1 was exponents. 7.2 is logarithms. And we will practice with these quite a bit before we move on to the next section, which is solving logarithms and exponents. So shoot me an email if you have any questions. If you have calculator issues, we can look at that in class. If you have to graph them, use Desmos. It's your best friend. And otherwise, I will see you soon. Have a great day.